So welcome and good morning to all the students present in this video lecture. Pascal's law states that the intensity of the pressures intensity of pressure at any point in the liquid at rest condition is same in all the directions. So first we need to understand the meaning of the sentences or the law of Pascal's. The intensity of pressures at any point in the liquid at rest is same in all the directions. Students, what is exactly the meaning? Suppose I have taken this one water bath or one pan of filling with waters, and suppose I'm taking any this point, so it has a directions like we have discussed about the three-dimensional. So the pressure is acting in this directions, in this directions, in this direction, in any directions. So the intensity of pressures in all the directions are equal if the fluid is at the rest conditions, means there is no motion, there is no motions. So this law is applicable when the fluid is rest, means it is applicable to the static conditions only, static conditions. It is not applicable for the dynamics, means whenever the fluid is having a certain motion, at that time you cannot be able to apply this Pascal's law. Pascal's law is applicable when the static fluid is there or fluid is at rest conditions. And the intensity of pressures means the value of pressure. So now we are going to derive. So before going to derivations, we just have taken one elementary area. So again, I'm taking the one pan in which the water is there. So I have taken this one triangular elements. So this triangle, I'm giving the name, that is the A point. Here it is the B point. Then here it is a C point. Let's say the dimensions, I enlarge this figure over here, the triangle. So this is the A, here it is B, and this is the C. This is my 90 degree. I'm considering this angle theta. So this angle is becomes the 90 minus theta. This side, which is a parallel to the x-axis, I'm giving the name that is a dx. Parallel to this y, I'm giving the name dy. And this is the length I consider, this BC length I consider as a ds, that is a surface length. And the dimension perpendicular to this paper, means this is a two-dimensional or the two-dimensional figure or the two axes we have considered. The perpendicular to the A means in the depth of this paper, so we consider this z axis is a 1. Like suppose this is actually it is this kind of triangle is there. For just idea, I will discuss this. So it is this kind of, so this side is a dx, this is the dy, and this length is es. This length, particularly this length or this length, that is called as a dz, and that is I'm considering as a 1. And I'm viewing this object from this direction, that is x direction, and that's why this figure is looks like in the two-dimensional. From the x view, there is dx and dy and ds. The perpendicular directions I'm considering as a unit. So suppose I want to calculate the cross-sectional area of this, then this length is 1 and this length is dy. So area of this hatching line area, the hatching line plane is dy into 1. Suppose I want to consider this another area, then it becomes a dz is 1 and ds is there, so ds into 1. So the here the concept is, whenever you are going to consider the perpendicular area, you have the dz value is 1. We are going to start derivation. Here the pressures exerted on the AB phase, that is in this phase, I'm taking as a px because it is in x directions. Here it is parallel to this y direction and perpendicular to x. That's why I'm called as a py. And the pressures acting over here on these S surfaces, that is at P, that is called as PZ, and which makes an angle with this normal. I'm plotting the normal to the surfaces, and this angle is of theta because this angle is theta. We also know that the force pressure is equals to the force per unit area or area. I'm going to use the Fx for the force as well, and for the pressure I'm using the Px. So there is no confusion in this. So now with these nomenclatures, I'm going to start the derivations. Px is a pressure and Fx is the force acting in x directions. This px is acting on the faces, that is face AB. This is also on the AB faces. Then py and the fy, that is the force and pressures acting on the surface, that is the AC. It is acting on the surface AC. Pz and fz is the pressures and force acting on the surfaces, that is the BC surfaces. We have to go for the balance conditions, but before the balance conditions I want to calculate the area of different surfaces so that it is very easy to understand. So I'm going to consider the area of the AB face. કોઈ કહી શકશે કેટલું થશે AB face area? This AB face, that is a dy, and the perpendicular dimension is 1. So we get the dy into 1 because the dz is 1. Then area of the AC face. Same way, what is the AC face? That is dx into 1 because this is the dx and perpendicular dz, that is 1. Then the area of the BC face, that is ds and perpendicular dimension is 1. So we get the ds into 1. Now I'm going to calculate the volume of the triangle or volume of the elements. So we know the concept of density. The density equals to mass divided by volume. So from that we can able to calculate that mass equals to density into the volume. And the volume of the element is, what is volume? Area multiplied by the height or the width or the depth. It is 1/2 base into height. So what is a base? Base is dx and height is dy. So we get the volume equals to area into length. So area is 1/2 base into height. So base is dx and the height is dy and the perpendicular dimension is 1. So we get this 1/2 dx into dy. Clear? Now we are going to calculate the weight. So weight W equals to mg and m equals to rho into v. So we get the rho vg, and v is already we have calculated. So finally we get the W, and W equals to the rho into 1 by 2 dx dy into 1 into the g. So finally we get 1 by 2 rho dx dy into g. We go for the balance conditions. Before going to balance conditions, I just want to write the expression of the fx, that is a force acting. Force equals to pressure into the area. So pressure is the px, and the area of AB surfaces, that is dy into 1. So I'm having the dy into 1. That is force acting on the AB surfaces. This is acting on the AB surfaces. Then fy means py into the area of the AC surface, and AC surface is having area of dx into 1. So we get the py into dx into 1, that is acting on the AC surfaces. Now for the z, so fz, I am getting the pz into the area, an area of BC surface, that is ds into 1. So I am getting this ds into 1, that is acting on these surfaces, that is a BC surface. So now from the pressure intensity, I have converted all these things into the force, and all the force is having a units of Newton. Similarly here, the mass is having a units of kg, into the g means meter per second square. So finally the unit of weight is also the Newton, and weight is acting on the cg means the center of gravity. So weight is acting over here, it is the W. Now I'm going to plot the free body diagram along with this force which is acting on this elementary area. W, which is acting on the CG, which is in downward directions. This is W. Here the force is acting, that is the Fx. Here the force is acting perpendicular directions in the upward direction, that is the P, or sorry, Fy. It is Fy. And the third is acting over here, and that is called as Fz. And the angle of this Fz with this normal is a theta, and this angle is also theta. Now we resolve this force, that Z force, in the two directions. Let we have already do these practices in the yesterday's lecture. Suppose P is there and this is a theta, then we get the P theta cos theta, and we get the P sin theta perpendicular to that. So here, when we consider in the horizontal directions, this force is resolved over here in these two directions. Let's say is F. So it making the angle with this vertical axis, and that's why it becomes Fz cos theta, because it is adjacent side, and here it is becomes Fz sin theta. So this component, this force is acting in these directions, so resolution is becomes like this, and here it is like this. So this is Fz, and this horizontal component is becomes Fz into sin theta, and the vertical component is becomes Fz into cos theta. So now we considering the balance or equilibrium conditions. So in equilibrium conditions, the horizontal forces as well as the vertical forces having a resultant of 0. So we analyze the forces first in the horizontal conditions. Horizontal force. So horizontally, one force is acting, that is X. It is acting in the directions from left to right, and the component of Fz, that is Fz sin theta, is acting from right to left. And for the equilibrium, both are equal. So we write that the Fx equals to Fz sin theta. And we know that this Fx minus Fz sin theta equals to 0. Now we are going to put the value of this Fx and Fy. So from previous expression, we know that Fx equals to Px into dy and Fz equals to Pz into ds. So we are putting down the value, that is a px into dy minus pz into ds into sine theta equals to 0. So we get the px into dy equals to pz into ds sine theta. That is our expression number 1. Now we are resolving the forces in vertical conditions. So vertical forces, so some of the forces are acting in the downward directions and some of the forces are acting in upward directions. So here the downward directions means the w is there, as well as the component of this fz, that is fz cos theta, and in upward direction there is fy. So we write upward forces equals to the downward forces. Upward forces equals to the downward force. So the upward force is only the Fy. So we will write it down, Fy equals to the downward force W plus Fz into cos theta. Now again we put down the value. So Fy, we already know that what is the value of Fy? That is a Py into dx. We have already calculated this value of W, that is the 1 by 2 rho dx dy into g, plus this fz means pz into ds into cos theta. So from this expression we again make the subject like this, the py dx minus pz ds sine theta equals to 1 by 2 rho g dx dy. We call this as expression 2. Now we go for the some geometrical discussions. In this triangle, that is ABC, we have this sign, that is AC is dx and AB is dy, and this is pz. So we again going to establish a relationship between that. This is a ds, which makes an angle theta. This is our dx and this is our dy. So we know that the AB, like this is AB and this is C. So AB is the adjacent side of this BC and AB is the opposite side of this angle. So the AB equals to, it becomes a ds into sine theta. And we know that the AC equals to the ds into cos theta because it is adjacent side, and AB having a value of dy and AC having a value of dx. So we know that dy equals to ds into sine. So here we have ds into sine theta, so we can write it as dy, and here it is ds cos theta, we can write as a dx. So here we have ds into sine theta. So we will put it down the value of this two expression over here. So we get the px dy equals to the pz ds sine theta is having a value of dy. And here the py dx minus pz, the ds sine theta, is having a value of dy. Sorry, we have here it is a cos theta. Here it is cos theta, so we have to write the cos theta. So ds cos theta is having a value of dx. So here it is a dx, which is equals to 1 by 2 the rho g dx dy. We have this dy is cancel it out. So we get the px equals to pz. That is our first expression. Here, students, the value of this dx and dy is very small. So the multiplications of dx and dy is very small. So we are neglecting this term, and this term is equal to the 0. So what we get, the py dx minus pz dx equals to 0. I carry out this term over here. So we get the py dx equals to pz into dx. So this dx is cancelled out. We get py equals to pz. So our final two expression is there, px equals to pz, py equals to pz. So we can write that from these two, px equals to py equals to pz. And what is px, py, pz? Px, py, pz is the pressure intensity in the directions of x, y, and z. Similarly, we can derive the value of pressure in any directions on these rest conditions of elements is having a same intensity. So that is the proof of the Pascal's law. We have started with this. Intensity of pressure at any point in the liquid in the rest condition is same in all the directions. And here we consider the three direction, and we derive that the intensity of pressures is equal in all the directions. So thank you for attending this lecture. Thank you.